Welcome to the next part of the module on Android concurrency frameworks, which covers the Looper class. This part explains how the Looper class provides a thread-specific event loop that waits for and dispatches messages to handlers and shows how loopers are applied in Android applications and concurrency frameworks. A looper contains a synchronized message queue that's used to process messages placed on the queue by one or more threads, as described at this link. This queue can be used to implement a thread-specific event loop, which is a key portion of an event-driven programming model where the control flow of the thread is determined by messages to corresponding user actions, such as touchscreen presses, sensor outputs, or messages from other threads, as described at these links. Only one looper is allowed per thread. This constraint is enforced by the thread-specific storage pattern, as described in an upcoming video. Multiple loopers can run concurrently in multiple threads and communicate by passing messages. The key methods defined by the looper class are prepare, loop, and quit, as shown at this path name. Prepare is a static method that uses the Java thread local class described at this link to initialize the current thread as a looper in accordance with the thread-specific storage pattern described at this link. Prepare must be called explicitly before running the event loop, followed by creating handlers that then reference this looper. The loop static method runs a thread's event loop, which waits for messages to arrive on the looper's thread-specific message queue. The call to next on the message queue can block waiting for messages to arrive, using the Linux epoll scalable I/O event notification mechanism, as shown at this path name. Once the next message is received, the loop method dispatches the message to its target handler. Note the inversion of control here. The looper runs the thread's event loop, and messages are processed via callbacks to handlers provided by application developers. Quit initiates the shutdown of a looper's event loop. Quit doesn't immediately terminate the loop, but instead it enqueues a special empty message that informs the looper to shut down when it processes this message. The actual task of managing the queue is done by a handler, which is responsible for adding, removing, and dispatching messages in the message queue to their intended targets, as described at this link and covered in an upcoming video. We'll now examine one way in which Android software uses loopers. By default, a Java thread, and thus an Android thread described at this link, which is a Java thread, does not have a looper associated with it. Therefore, if a thread needs looper behavior, one approach is to program it directly into the thread, following the steps shown at this link. For example, a canonical looper use case appears in the video editor activity covered earlier in the Java semaphore video. This activity contains a private class called PreviewThread, shown at this path name. The first step in making PreviewThread a looper is to extend the Java thread class. The constructor of PreviewThread then starts itself to preview videos in the background. When PreviewThread is started, its runHook method performs the next step by calling looper.prepare, which initializes the current thread as a looper. The step after that involves creating one or more handlers to process incoming messages. The final step involves calling looper.loop to run the event loop, process messages, and dispatch callbacks to handlers until the looper is explicitly told to stop by calling its quit method. Although we show these steps in the context of the video editor activity, this approach is applied to add loopers to threads throughout Android middleware and applications. Now that we've shown the key methods in the looper class and outlined a canonical application of this class in Android, we'll show several examples of how Android's concurrency frameworks use loopers for both the user interface thread and background handler threads. The user interface thread has a looper that it uses to receive messages from itself and other background threads, as described at this link. The message queue in the user interface thread's looper helps serialize access to user interface components such as views and menus, and ensures that only objects running on the user interface thread have access to other objects in that thread, as described at this link. The user interface thread's looper is implemented in the activity thread class, as shown at this path name. Activity thread's main entry point method calls prepare main loop, which initializes the current thread as the application's main looper. The Android runtime environment creates the main looper for an application automatically, so there's no need to call this method directly. Loopers can also be defined and used in non-user interface threads, as found throughout Android's frameworks, applications, and providers. Their methods are typically called from within a run hook method that performs some type of service in a background thread. This use case is such a common idiom that Android defines a helper class called handler thread, which starts a new thread containing a looper, as described at this link. The handler thread class uses the template method pattern described at this link to perform the fixed prepare and loop steps in the handler thread's run template method algorithm. Subclasses of handler thread can create their desired handlers by overriding the onLooper prepared hook method, which plays the role of the primitive operation in the template method pattern. The handler thread start method must still be called explicitly to spawn the thread, which invokes its run hook method, as shown in this example from the Android intent service, which handles asynchronous requests, expresses intents on demand, as described at this link and covered in the next section of this MOOC. Handler threads are used extensively throughout Android's frameworks, applications, and providers. In summary, a thread can be programmed to contain a looper, which in turn contains a message queue. These objects collaborate to provide applications with a thread-specific event loop that waits for and dispatches messages to handlers in the user interface thread or in background threads. A looper is often invisible to application software components, which typically access the user interface thread's implicit looper via handlers, as described in the next two videos in this module. Explicitly programmed loopers are typically used in background threads by applications that need a more sophisticated concurrency model than the default single-threaded model, described at this link. As shown at these path names, loopers are used throughout Android's open source applications, application frameworks, and core concurrency frameworks. In particular, loopers play an essential role in providing inversion of control to Android's Hammer and Async task frameworks.